Let's look at some more exponential equations where we have to use some more tricks up our sleeves. When we have 32 to the x equal to 8, we start by looking at the smaller number, 8. We know 8 to the first is 8, so we don't really care. But if we do 8 to the second, that's 64. 64 is way too big because we're looking to rewrite the 32. So let's think about how we can rewrite 8. Well, we know that 8 is divisible by 2. Can we rewrite 8 as 2 to a power? Well, we know 2 squared is 4, and we know 2 to the third is 8. All right, so we just found that 2 to the third is equal to 8. All right, we got lucky. We can rewrite 8 as 2 to a power. Can we rewrite 32 as 2 to a power? All right, we have 2 to the third is equal to 8. 2 to the fourth gets us 16. 2 to the fifth gets us 32. Awesome sauce. So we know that 2 to the third is equal to 8, and 2 to the fifth is equal to 32. So let's rewrite our equation. We had 32 to the x is equal to, I'm going to rewrite my 8 as 2 cubed. And again, that was because we found 2 cubed is equal to 8. And then we found that 2 to the fifth was equal to 32. So I can rewrite my 32 as 2 to the fifth raised to the x equal to the 2 to the third. And that's because my 2 to the fifth was 32. And now you have to remember some exponent rules because we have an exponent raised to another exponent. You get to multiply them. So 5 to the x, or 2 to the fifth raised to the x, becomes 2 to the 5x. And the reason for that is because of our exponent rule. If you have x to the a raised to the n, that becomes x to the a n. Okay, and now notice that we have 2 to the 5x equal to 2 to the third, which means the bases are the same and they go away. And that again is from the one-to-one property of our exponents, or of our exponential equations, which means we have 5x is equal to 3. And when we divide both sides by 5, we get x is equal to 3/5. If you wanted to double check your answer, the left-hand side where we have the x, so we have 32 to the x, that would become 32 to the 3/5. And if you double check that in the calculator, 32 to the 3/5, we do get 8, which is what we were looking for. So our x to the 3/5 works. In our next example, we have 9 to the x is equal to 1 all over 27. If we follow our original rule and start trying to rewrite 27 as 9 to a power, 9 to the first is 9. 9 squared gets us 81. Way too big when we're looking for 27. So let's think about how we can rewrite 9. Well, 9 is not going to be 2 to a power. So looking at the first odd number other than 1 is 3. 3 to the first is 3. 3 squared gets us 9. So we're getting somewhere. So 3 squared is 9. Now let's go back and try to rewrite 27 as 3 to a power. We just did 3 squared, so let's try 3 cubed. 3 cubed gets us 27. All right, so let's start rewriting these. Instead, I'm going to start with the 9 since we found the 9 first. So instead of 9 to the x, I'm going to have 3 squared to the x equal to 1 all over 27. And again, that is because 3 squared is equal to 9. I can rewrite the left side as 2 times x in the exponent, so 3 to the 2x. And again, that's because of our exponent rules. Same one we discussed in example 4. If you have x to some number raised to the m, that is equal to that number times m. I think I used a and b or a and n in the last one. So we have 3 to the 2x is equal to 1 all over. Now I'm going to rewrite that 27 as 3 cubed. And again, that is because we found that 3 cubed is equal to 27. We can't just cancel our base 3's because we have a big 3 and a little 3. This 3 from the denominator needs to come up. Remember, to do that, we need to change the sign on the exponent. And that is from our exponent rule of if we have x to a negative number, that becomes 1 all over x to a positive number. And this works forwards and backwards. So if it's in the bottom, we can move it up as long as we make it negative. And we have 3 to the 2x is now equal to 3 to the negative 3, which means that we can get rid of the bases because the bases are the same, which means that we have 2 to the x, or sorry, 2x is equal to 3. Divide both sides by 2, we get negative 3 halves. And if you want to double check your work, on the left-hand side, we had 9 to the x. Now, plugging in for x, we would have 9 to the negative 3 halves. So 9 exponent negative 3 halves, convert back to a fraction, and we get 1 all over 27, which we had on the right-hand side of the equation. So x equal to negative 3 halves is our answer. Number 6. We have 8 and 16, so at least both numbers are big, no fractions, but they both have x's. You know what's going to change? Nothing. Nothing is going to change. It's all the same. So if we try to rewrite 16 as 8 to a power, I know that 8 times 2 is 16, but remember, we're not doing multiplication. We're doing powers. We're doing exponents. So if I do 8 squared, I get 64. That doesn't really work for us. However, remember in a previous problem, we found that 2 to the third is equal to 8. So I'm going to write that down so we don't forget it. Let's try to rewrite 16 as 2 to a power. 2 to the third gets us 8. 2 to the fourth gets us 16. All right, so here we go. Instead of 8, I'm going to plug in a 2 to the third. So instead of 8 to the x plus 3, we have 2 to the third to the x plus 3 equal to 16 to the x minus 1. And that's because 2 to the third equals 8. For our exponent, Remember, if we have an exponent raised to another exponent, that means we're going to multiply them. Okay, so we have 3x plus 3 to distribute all the way through, which gets us 2 to the 3x plus 9 equal to 16 to the x minus 1, because we had to distribute that 3 all the way through the exponent. Okay. And now we have 2 to the 3x plus 9. And on the right-hand side, I'm going to rewrite that 16 as 2 to the 4th. And you may be wondering why I didn't do that earlier. I'm going step by step. If you wanted to write our 2 to the 4th, oops, sorry, technical difficulty. If you wanted to write our 2 to the 4th all the way back at the beginning, you could. It's just I did not want to do too many steps at the same time, so I left it. Okay. So continuing on, we've already done the left-hand side. Right-hand side, we need to take our 4 times our original exponent of x minus 1. And remember, we're going to distribute all the way through. Left-hand side staying the same. Right-hand side, the 2 as the base stays the same, but we get 4x minus 4. So 2 to the 3x plus 9 is now equal to the 4x minus 4 because of the exponent rules. And because our bases are the same, the one-to-one property of exponential functions says that we can get rid of them. Rid of the bases, not the exponents. But we do know that our exponents are equal. So 3x plus 9 is equal to 4x minus 4. If I subtract 4x over, I have negative x plus 9 is equal to negative 4. Subtract the 9, I would have negative x equal to negative 13. Divide both sides by negative 1, and we get x is equal to 13. If you wanted to check this answer, we would have to check both sides. We would have 8 to the x plus 3, which gets us 8 to the 13 plus 3, which gets us 8 to the 16. Let's find out what 8 to the 16 is, if our calculator can handle it. Okay, really long number, that 10 to the 14 means that we need to move that decimal place 14 places to the right. And if we check our other side of the equation, we would have 16 to the x minus 1, which would be 16 to the 13 minus 1, which gets us 16 to the 12. And you may think that, wait, those aren't the same. But if we go back to our calculator and we check what 16 to the 12 is, we get the same really gross number. So x to equal to 13 is our answer. One more. And this one you have to remember a radical rule. It says that if you have the nth root of x, this becomes x to the 1 over n. So for example, if I had the 5th root of x, that would be x to the 1/5. If I had the 11th root of 13, that would become 13 to the 1 over 11. If I had the 64th root of 2, I would have 2 to the 1 over 64. Okay, so back to our problem. We would love our bases to be the same because they both have big 7s, but there's that radical in the way, which is why we're going to use this radical notation rule to rewrite a radical as an exponent. Left-hand side stays the same. Right-hand side, remember, if you can't see the index, it's a 2. So we're going to have 7 to the 1/2. And now, because our bases are the same, we can get rid of them, which means our exponents better be equal. We have x minus 2 all over 6 is equal to 1/2. Now, back in the day, they used to solve this using cross multiplication. My students are telling me now that that is old school. It is now called something along the lines of the butterfly method. And if you really want to go old school, you would find the LCD of both sides to clear out your fractions. But cross multiplication says if we take 2 times x minus 2, that better be equal to the other side multiplied, 6 times 1. So we have 2x minus 4, because distributing the 2 through, equal to 6. Add the 4 to both sides, we get 2x is equal to 10. Divide by the 2, we get x is equal to 5. If you wanted to check your answer, we would have 7 to the x minus 2 all over 6, which would get us 7 to the 5 minus 2 all over 6, which is 7 to the 3 over 6, because 5 minus 2. And we could reduce this as 7 to the 1/2. If we check 7 to the 1/2 in our calculator, we get an icky decimal. Not too icky, 2.64575. And we need to see if that's equal to the square root of 7, which is on the right-hand side. Because the two decimals are the same, our x equal to 5 is a good